If I can get this to work correctly. Probably not. Is that working good? Okay, so I'm going to talk about CGNS parallel decomposition. I work at Sandia Labs. We do a lot of finite element, finite difference type work. We have meshes modeling these structures that are either structured meshes or unstructured meshes. And I, for some reason, got them wrong on this, where you see unstructured CGNS, read structured CGNS. We have a couple ways that we can do that. We can either feed this entire mesh up to this parallel analysis code. They're running on anywhere from 1 rank up to 100,000 ranks using MPI and GPUs. And so to be able to do these efficiently, we want to be able to spread this mesh, which may be billions of cells, evenly across all of these ranks, such that each of these MPI ranks or GPUs is doing about the same number of, working on about the same number of cells. And so we have to come up with a way to decompose this mesh across, so each of those ranks is equal. So there's 2 ways. One way, the easiest way, is to basically just say, feed the entire mesh into the application, decompose it on the fly, and run. There are some legacy times in where we actually pre-decompose. So if we're running on 100,000 ranks, there'll be 100,000 separate little files. And then each rank reads a file individually. And then we have the same thing with the unstructured. We use, I'm going to only be talking about the decomposition method for the structured meshes here. How does this relate to HDF5? Basically, CGNS uses HDF5 underneath. THG, the HDF group, supports the development of CGNS. And then once the model is decomposed, we use HDF5's parallel read-write capabilities to give us a very efficient way of getting that model in and getting that model out. Requirements for this decomposition is we want to distribute this work evenly. We want each rank, or MPI rank, or each GPU to have about the same amount of work. You don't want one to be very, your total job throughput is going to be limited by the slowest rank. And so you want all of those doing about the same thing. During the decomposition, we don't want to be doing all this communication. We want each rank to be able to know, okay, this is my mesh, this is what I'm going to work on, and don't have to talk to anybody. During the analysis, you are going to have this communication, but we'd like to be able to get rid of that during the decomposition. And we don't want that we want the decomposition to be dependent on the number of zones that you have in your mesh, but not the individual cells. Zones are on the range of 1 to maybe 100 or 1,000 zones, whereas your ranks, your cells are on the, can go up to billions or tens of billions of cells. And for when you're actually, after you've got the decomposition, you want it to be very memory efficient. You can't run this by reading the entire mesh up on rank 0 and broadcasting it across to all the ranks. You want each rank to be able to handle about, if you can run, if a rank can hold M cells, you want your 100,000 rank job to be able to handle 100,000 times M cells. So we want this to be able to scale well, and we want it to be very invisible too. We want, so when you're running the analysis, you don't have to create your input file such that it knows how many ranks there are or how many ranks is going to be run across, because you may get, I can run on this machine now has 50,000 ranks available. Let's throw it onto that machine and run as quick as possible. And so we want it invisible, but if there are problems, we want to be able to dig down in there and see what we're actually doing. What happened? Okay. This is based on, at Sandia, we use this thing called the IOSS library for most of our finite element codes. It's sort of a database independent interface to the application codes. The application codes basically write to an IOSS interface. It takes care of knowing whether underneath we have CGNS, Exodus, Catalyst, all these different formats. And so it basically makes it much easier for us to write analysis codes or post-processing codes because they don't have to know whether we're doing CGNS or HDF or Exodus or any of these types of things. The basics of the decomposition algorithm, we basically say, this is the model, decompose it over this number of ranks, and I want this goodness of decomposition. And so we calculate that we want to decompose such that if you are perfect at perfect decomposition, the number of cells divided by the number of ranks would give an average work. And we want that to be plus or minus this goodness of decomposition. The way the algorithm works is we first pre-split, we give the algorithm at least, so if you're running on 1,000 ranks, you want at least 1,000 of these little bitty zones that you can throw to places. So we'll pre-decompose or pre-split the model into at least that number of zones or child zones, and then we'll assign them to ranks. And if the load isn't quite balanced, then we'll start modifying those. We'll split them more. So in the pre-split, you just kind of go, okay, this zone, which has about this much work, we want it and divide it by what the average work we're aiming for, and that will tell me about how many times to split things. And if this was all done in floating point, everything would be good, but we're an integer, so you have to, nothing's going to come out perfectly. And so once we get enough of these zones split into smaller zones, then we can start, then we can go on to the next part of the rank. It's nice to be able to get the number of splits to be a power of 2, because if you say, okay, I want to split this big zone into 8 pieces, you just split it in half, split it in half, split it in half. Where you get some weirdness going on is if you go, okay, I have to split it 3 times. So how do I split this rectangular zone into 3 times? So basically what we do when we split a zone, if it says if we're splitting into factors of 2 or powers of 2, we just split it in half, split in half, split in half, like I said. If we're splitting into such that it's not a power of 2, we'll then kind of split off such that what we have left can be a power of 2. So like on the blue here is the power of 2 one, the brownish one is sort of power of 3. We try to keep it as like as squarish as possible. So like I said, on this one, we just split in half and we get two children that are 8x4, 8x4 on this, where we started out by 8x8, and then those can be just split in half, 4x4, 4x4. We're aiming for an average of 16 work on that, and we end up with 16 on each of the ranks, and so we've got a perfect balance. If we're trying to split this same mesh over 3 ranks, we want to try to get 21 and a half work per rank. That's not going to work. We first split into an 8x3 and an 8x5, so that gives us 24 on one, and then we've got 40 left over, and we can split that 40 over. So now we've got a 24, a 20, and a 20 as our work, and we're aiming for 21. So we're close, but we don't, that's about as close as you can get with this smallish type thing. When we split a zone, each split zone is going to know who its atom zone is. That's sort of what the original model that you read in comes in with, atom zones. And then they get split into children, and each child has a parent, and because you may split a child into a child into a child, and you have to be able to reconstruct this such that when you feed it to the analysis code, all it knows about are the atom zones that it started out with in the original model. And you have to be able to relate back onto that. And then we add some communication. So when you split a zone into half, it has to know, to be able to communicate. Rank 1 would need to know, I need to communicate with my sibling who is over on rank 2. And that's where we add these zone grid connectivities, which are abbreviated CGCs. And that tells the application how to communicate to these other ranks. And then if there was already some communication, say you had a 2-zone problem that you're reading in, those existing communications also have to be propagated down to the children. So here's another sort of that same thing. We're trying to get 16 average work on the left side there because we're splitting over 4 ranks, or we're splitting that same rank over, it should be 64 divided by 3 on the right side. So on the left side, we just split it in half and half. On the right side, we kind of split off that one part again. And now we have to know. So that's kind of our distribution there is. So that's what it kind of looks like. And then now we have to say, okay, we've got these zones split. How do we assign them to ranks? And we basically just sort from the most, each of our child or the bottom level child ranks, we sort them based on the amount of work that they have. We just start assigning them sort of in a greedy method of each start assigning to the ranks as we go. Once we get all of those assigned to the number of ranks that we have, then we start filling in the remainder to try to say, okay, this rank still needs some work, so let's throw some of our remaining zones to that. And you'll find when we get to the end of that first assignment, we'll go, okay, we've got a few ranks that are way over subscribed. We've got a few that are undersubscribed. So if we're outside of that goodness factor, we'll split the largest zone that we have in 2, and then we'll start this assignment again. And we'll keep iterating on that until we get it such that all of our ranks have about the right amount of work assigned to them. So this also works like the ones I've shown in the previous just had started out with a single zone. This one is with a double zone. We're trying to get an average work of about 24 per zone. So we split the first one, split off this work of 16, which leaves 48 to be done. We can split that in half and get 24 on each of those. We now look at the first original green zone there, and it had too much work, so we split off some work on that. And now we want to assign these to ranks. So we'll assign, as shown there, rank 0 will have 24, rank 1 has 24. So basically we ended up with a perfectly balanced there. We've just got, and so it's hard to kind of do this with small numbers of ranks and small zones because but once you get into these bigger things, it goes much faster kind of. The other thing is we have some special options. Is some of the analysis codes say they have what's called a line solver, where they can go through a column of cells, but they want all of those cells to be on the same rank. So they will tell us beforehand, only this surface here, do not decompose as the cells go into that surface. Keep all of the cells in a column that are going along a column off of this surface on the same rank. And so that's like this, they said they want that top surface is where my lines or cells are all going to start. And so we just decompose this way such that it makes it much faster. It's hard to know what your goodness of a decomposition is. So we have a code called CGNS Decomp. It will tell us how the decomp works. It actually can run on a serial machine. This is sort of one mesh we started with. It has 14 zones over 11 processors. So it basically just tries to assign these all in. And if you look at the histogram, it's not very good. The maximum work on a cell is on a processor is 128, the minimum is 32, so that's a ratio of 4:1. So then we say we want a better decomposition. We make the load balance factor a lot smaller. It now starts splitting some of these zones into subzones, assigns those to ranks, and we get a much better distribution. In the past, we had the previous one, the maximum work was 128. We've now down to the maximum work is 96, which is a much better, we're only like 3% over what the perfect decomposition would be. In addition to these workflow applications, we do have some applications that will write out a single rank per file or single file per MPI rank. And the CPUP actually, they'll put them back together into a big file at the end. We can also create our convert our structured meshes into unstructured meshes using other codes. And so those are used by some of the other applications or the analysts during their workflows. So basically, we've got an algorithm that we came up with for efficiently decomposing these structured CGNS models across anywhere from 2 to 100,000 ranks. It's been used in our production CFD codes for several years. It's been used on models with up to billions of cells and on, like I say, hundreds of thousands of ranks. In the future, we want to be better affinity when we split these zones. We want to kind of keep them such that the communication paths are minimized, and we also may want to make it such that zone 0, if we have a zone that's doesn't have as much work as the other, make that one zone 0, since zone 0 sometimes does other stuff of logging and things like that on some application codes. We're looking at what will optimize this better for GPUs, since they have some slightly different needs than splitting over regular CPUs. We also just want better control over some of the decompositions, but it's been working very well for us over the past probably 5 to 10 years that it's been in production. Thank you.
Good one. Last night on the speed on Zoom will not be working the same here. So
one of the decompositions we were showing, log 32, and we showed that split into 24 and 8. Why is that? What about the use? It's not better than splitting it into 216.
Because we can then put that 8. So we want, it doesn't, a per zone doesn't have to have, with the 8, the 24 gave us what we were aiming for. We wanted the average work to be at 24. So that gave us, we could fill up a processor with 24. And then there was an 8 and a 16 from another zone. Then we could put the 8 and 16 together on a rank, and then they would also have 24. So it gave us more of a perfect overall balance, even though one of the processors now had a zone 1 and a zone 2, but the overall work on that processor was still balanced better. So, thank you.
Exactly what is it? The data quantity, or is that a computation?
It's a computational zone. It may be a material type or something like that. So if you're in a rocket, one of the zones may be a nozzle, or one of the zones may be a shroud or something like that. They're different materials or different pieces of your overall initial model that's coming in. So they're physical, they're not necessarily they're physical type things that will have a certain material property or certain boundary conditions or something.
Do you have situations that a ramp access multiple zones?
Excuse me?
Do you have situations that a ramp access multiple zones?
Yes.
And do you have crossroads access and reading rights of this kind of thing?
Sorry, I'm not understood.
Okay.
I don't hear real good. Yeah, there's a echo and I can't hear real good. So. But we can talk during the break.
other questions? Okay, thank you so much. Thank you.